Okay, great. So we can get started then. So good afternoon, everyone. Welcome to this edition of the NITheCS Micro-school. My name is Dean Brand, and I'm a second-year PhD student at Stellenbosch University, working with Professor Francesco Petriccione, who's the director of NITheCS. And on his behalf, I'm hosting this episode of the Micro-school, and I would like to introduce you to today's speaker, small Tshithavhana, who is a master's student at the University of Witwatersrand in Johannesburg. He originally completed his undergraduate studies at the University of Venda, majoring in maths, physics, and computer science, and is now doing research in data science for banking and fraud detection. So he is the best person to be teaching us about data engineering today. I'm very much looking forward to the presentation. I hope you are as well. If you have any questions, please feel free to ask them in the chat. And with that, I hand over to you, Small, to get started.
Thank you very much for the good introduction. So in this micro school, I'll just be taking you over a broad overview of what data engineering is, and more specifically, we'll be diving into big data and the most important tool of analyzing big data, which is Apache Spark. So the agenda is simple. I'll just give you an introduction of data engineering, and then take you through big data and what actually scaling up big data is, and parallel processing, and also Hadoop, the Hadoop architecture, and also Databricks and Apache Sparks. And by the end of this presentation, we'll just do a mini hands-on with how to work with Apache Spark and Databricks. So what exactly is data engineering? So this is just a basic process of just looking or combining the process of extracting data from its raw data source, and also analyzing it or giving it to the end user, whether it be some business analyst in a bank or in a corporate environment, and also just data scientist or any researcher who wants to analyze the data or do some research or perform or actually extract meaningful insights from that data. So it's actually a combination of the two when it comes to the real industry within the business and actually the research part of it. Because when it comes to the machine learning side of it, we mostly extract data from a raw data source, whether it be our tools for computer vision, taking pictures and actually storing the data and performing some computer vision tasks such as for image recognition or image detection. So we usually collect data in an unstructured way, where you have different formats such as camera, video data, voice data, text data, audio data. And then we usually put it in a place called a data lake, which is a centralized system where you can put all of your data, whether it be unstructured or structured. And then you perform the ETL, which is just an extraction of the data, transforming it, and then loading it. And then afterwards, you can just perform your machine learning task. And from the business side of it, most data is stored in a cleaned version or in a structured way, so that they don't have to actually do the whole process of putting it all together or structuring it. So they usually hire external companies to structure their data so that they can just do the extraction, transformation, and loading process, and then put it into their localized system, which is their data warehouse, and then perform some business intelligence through dashboards or apps. So this entire framework or this entire view describe what data engineering is. So from the back end, it's actually collecting the data and structuring it. And then from the front end, it's actually performing real task analysis of the data. So you might be asking yourself, why is it important? Well, the problem with the model, like the model or the modern idea or the mode, like how people view data these days, is that they're always too trusting of it, where you have a researcher or a scientist getting the data from a data source or whether the internet, and then they can actually do good research using their methodology. But since they don't know where the data comes from and whether it's structured or unstructured, they don't know how it came about, or whether there was some bias or error which was performed through the data extraction. So it's actually a good thing or a good skill to know where your data is coming from, to structure it, and then at the end of the day, you can actually know with certainty that you are getting good results from your research or good results from your business. So a part of working with big data or data engineering is collecting data from its raw source, meaning that it's coming in a large amount of volume. And in this section, we'll just be looking at the term big data or what it is, because most people look at it as just working with data which has millions and thousands of rows. But actually, the term big data it's a it's a term used to describe a collection of data sets where it becomes too complex or it becomes too complicated to analyze due to how unstructured it is, having different formats and having different or large amount of data, or like how big it is and how complicated it is, in such a way that you cannot really analyze it using the most or a traditional means such as Excel or or any um, or any spreadsheet methodology, such as the Apple or numbers at the Apple version of Excel. So it becomes hard to actually analyze big data because of how complicated and how complex it is. So how exactly or how much is big data? So just to give you context, Google loads up to, or it collects 20 petabytes of data on a daily basis, and eBay collects 6.5 petabytes of user data on a daily basis. And also the CERN Super Hadron Collider collects 15 petabytes of data on a yearly basis. So you can imagine that it becomes hard to actually analyze or to do some meaningful insights or research from that data using the traditional means, due to how slow the system that we're currently using is, since it's usually or built up for data which is in the thousands. So big data can usually be described using the 3 V's. The first one being the volume, which just describe the scale of the data. Sorry. Which just describe the scale of the data. So for context, the digital universe, ever since it started in 2009, we had 0.2 zettabytes of data. And now we're working with 35.2 zettabytes of data in 2020. So we actually, the number of, or the volume of how data is increasing is exponentially with a multiple of 44 per year. And this actually means that any or your average company in the modern day is having, or it's averaging a collection of a zettabytes of data on a daily basis. And the second one will be the variety, which is how complex the data is. So you can imagine how, if today we have different data types such as text data types, numeric, audio, and video. So actually storing those data types in one place and actually analyzing it becomes complicated because of, or due to how different they are. And with a modern innovation with the Apple Vision Pro, which does a 3D map of of your screen, or also taking 3D version when it comes to the video. You can imagine that they are no longer using the standard video format. They had to create a new complicated format, which is encompassing, or which is combining all different technology at the same time or at the same place, which in turns makes it more complicated to analyze or to do research on. And then the third one will be the velocity, which is the speed in which the data is moving. So you can imagine how when you're in a very fast in the data moving industry, it's the two examples being when you're forex trading, how data is moving, or how you're analyzing the high speed data. If you miss, if you are a minute, if you delay by a minute, or your technology is not fast enough to analyze the data, then you're missing a lot of opportunities. And one of the major advancements which happened this year was that a group of scientists in Japan actually broke the data transmission record with during their research, where they transmitted approximately 23 petabytes of data in a second. So how fast the data is moving and how fast we actually capture the insights from that high speed moving data is actually a big part of big data and big data analysis. So the challenges which comes with handling such big data is very commonly the lack of software, because we don't have enough resources to actually analyze the large amount of data and also analyze their complexity. And one of the major challenges will be, or 11% of it will be people already using their or the technologies that they have, or the failure or resistant to change to a new technological software, and also the lack of skills when it comes to working with big data. Because unlike the common platforms for handling data, it really needs you to go in depth and research how to analyze it, how it works. Unlike if you can just take a short course within Excel to just learn some user-defined functions, or to learn some built-in functions within the platform. So those are the limiting factors when it comes to handling big data. And for researchers or big companies, one of the major limitations which comes with handling big data will be the hardware that they use, which is, suppose that you want to handle or you want to analyze a data which has 30 million rows. So your computer, or the computer that you have, is actually limited when it comes to the memory, the processing speed, and also the hard drive. Meaning that it's most likely, if it's not gonna crash, then it's most likely gonna take a long amount of time to run that individual program. And you can imagine, if you didn't do your coding right, or if the coding crashes, you have to take another or a long amount of time just to run the same program in the same amount of data. So to solve this problem, there's two approaches, which is scaling up the machine. So you can imagine this as, suppose that you have one of the institution, whether it be Wits or Stellenbosch, it hires one of the greatest scientists alive, maybe Isaac Newton um, or Albert Einstein. So they hire Isaac Newton to their math department so that since he is very, very smart to teach everything or to teach every course within the math department. So if the curriculum changes, they ask him to learn another part of the math branch, supposed to be calculus, and then they want partial differential equations. He goes and learns partial differential equations. So the problem with this is that we have one machine or one person learning or growing up or constantly scaling up, scaling up, scaling up, scaling up. At some point, that person is not gonna handle, or the machine won't be able to handle that much when it comes to the computation or learning. So instead of doing this, one of the best solution is actually scaling out, which is just having multiple computers doing, or multiple computers connected doing the same task, or distributing the one task on multiple computers. So for our example, you can think of it as having different lecturers teaching different courses within the math department. So at the end of the day, they're going to complete the task efficiently because each and every one of them is focused on their own task. So there's two architectures when it comes to this type of computation. The first one is the shared disk architecture, and the second one is the shared nothing architecture. So when it comes to the shared disk, we have two computers or nodes sharing the same disk memory. So we'll have data, and then we'll just divide the task through the different computational power with the different CPU. But the problem with this architecture is that if something happens to the disk, then the entire system is going to fail. So the solution to this comes through the shared nothing architecture, where we have different disks, we have different nodes, which are these ones, where we partition the data throughout the entire cluster, which is just the combination of different computers. So, and the upside of it, or the major difference, is that for each cluster has its own CPU and its own RAM. So that whenever one cluster fails, then we can just replicate the data which came from this cluster through to another one. Or if one cluster failed, we're not gonna lose the entire, if one node, sorry. So this is actually a node. So a combination of nodes they make up a cluster. So if one node fail, then the entire cluster won't crash. So this is the upside of the shared nothing architecture, which actually helps when it comes to data locality, where you don't have all your data in one place. So there's this Hadoop actually is one of the big data softwares which is using the shared nothing architecture due to its upside when it comes to not losing a large amount of data, and due to its distributed computing, or distributing all of the work throughout the entire cluster. So what exactly is Hadoop? So since we usually working with a large amount of data, so instead of sending the data into our computer and then performing some task to it, so Hadoop actually sends the program into the cluster, and then we perform tasks for that. We perform tasks and then we retrieve the results back. So hence this code which says if you can send the data to the program, then you send the program to the data. So Hadoop does this. So we have our cluster, and then we have our message. Oh, sorry. So we have our cluster, and then we have our data, which is distributed, which is separated all around the cluster. So Hadoop is going to send a task through the cluster, and then it performs a task called, or it uses an approach called MapReduce, where it maps all the tasks throughout the entire, it maps the task through a function throughout the entire cluster, and then it shuffles, it does the shuffling process, and then it reduces the results and aggregates the results for all of the clusters or all of the nodes, and then it retrieves the result. It retrieves the results back to the end user. So that's it. And Hadoop was actually the first open source products when it comes to big data. And now it's commonly known as the MapReduce because of how you can think of it as a basket. So it actually started small, and then a lot of applications started being added to it, such as they wanted to do more machine learning tests. So they created Mahout, and then they wanted more streaming when it comes to working with the data. And then they added Storm and Flume. So when it comes to Hadoop, it's mainly separated. You can mainly look at it as it's how it handles its file, which is the Hadoop distributed file system, which is just it for each big data that you have, it distributes the file equally throughout the entire cluster, and then it manages it. And how those, suppose that you send a task or a program, the resources or the management of how the resources are being executed or how each task is being executed goes through the program called Yarn, which is named after like yet another research is it navigator? Yeah. And then this is the MapReduce, which is just handling all analysis or any test that you give up. And we have Kafka, which is the streaming service. And then we have Flume, but mostly we're gonna be focused on Spark. This is the pink sided or the pink block, because you can look at Spark as the more modernized or better version of MapReduce because of how simple it is. Because originally MapReduce was created in Java, and now as compared to MapReduce, Spark actually uses you don't need to actually code in Java. You don't need to know Java. So Spark, you can actually use Python, you can use SQL, and you can use R, R programming language. So Spark actually integrates different languages within its platform, and it's better when it comes to handling big data and actually keeping everything simple, since you don't need to know a lot of things about when it comes to the Hadoop ecosystem and when it comes to distributed computing or parallel computing. So the core APIs when it comes to Spark is Java, Scala, SQL, which is the extraction of the data, and also Python to perform some of the machine learning tasks, and R. And then we also have the streaming and the machine learning task, and also the graphical computing task when it comes to the Spark environment. Sure. So the Spark environment or the Spark itself follows an architecture called the master slave architecture. So you have a master node here, and then you have different slaves which perform. The master will extract the data or from its main data source, and then it will distribute the work to the slaves on what to do or on how or what to do. And where you can look at the slaves as those nodes from which you can look at it as the shared nothing architecture as well. And it's actually good because also like the shared nothing architecture, each node has it actually stores so you have you have your main data coming from the data source or data file system or Hadoop distributed file system. And then the data is distributed equally throughout the workers or the slaves. And then for each slave or each worker, we are going to temporarily mount the data so that when we're performing a test, we don't really have to continuously go back to the main data source. So we'll have a task, and then since the data is stored temporarily, we just need to access it to our nodes or through our cluster temporarily, and then afterwards, if there's not enough inactivity or the the data is unmounted in a way. So what's the upside of using a Spark or PySpark, which is the Python version of Spark, as compared to to our traditional ways of analyzing data, which is the Python pandas. So unlike when it comes to the efficiency or the performance, PySpark actually it's good when it comes to working with big data and working with distributed system. And the problem with pandas when it comes to the performance is that it only works on a single machine or only for small to medium-sized data sets, which are thousands and at most millions of rows. And with this distributed or parallel computing, which comes with Spark, we can actually work with multiple data sets or a large amount of data set at a large pace, unlike taking a long time to run one program or one machine learning program because of how big the data is. And we can actually scale up PySpark when it comes to the data processing. And the upside also is that PySpark handles or is able to handle real-time data stream or data which is moving in a sequential format continuously, unlike pandas which can't handle real-time data processing capabilities. So when it comes to the memory consumption, Spark actually follows an approach called the lazy evaluation approach, which is just if you have your data, it's going to take the data from the data source and then temporarily stores it into its cluster. And temporarily stores it into its cluster. And whenever you perform any task, it's going to do the function, and then it's not going to do the function immediately. It will do it, but the function or the task is actually done. So at first it's going to optimize the way that it does the task, and then up until you request for the results, it's going to trigger the test to be done. Unlike Python, which will take a large amount of memory for the analysis when it comes to the memory consumption of a large data set. But the downside of using PySpark will be you will need to learn a lot of background, or you will need to have a lot of background when it comes to distributed computing. Unlike Python, which has a lot of APIs available for it. So at the end of the day, we can look at it at this way. You have PySpark, which you can look at it as a block of Legos, because it has all of these different resources and tools that you have at your disposal. But if you don't want to build a big system, or to just monitor your data at real time, to do tasks constantly, you can also, or the upside of it is that the people who develop Spark or PySpark, they actually created an environment called Databricks, which is just an environment which is simplified, which is just for you to learn PySpark or to learn Spark and to create a cluster like at any time. And it's all working. It doesn't need you to have a big computer. It just needs you to have a good internet access. So this is Databricks, and you can just create a cluster. And the good thing is that the cluster, there's a free version of Databricks available for anybody to use. And the cluster actually works very fast for a free version of it. So summarizing everything, so data engineering is a combination of tools, which is, when it comes to the data side of it, will be you're taking unstructured, semi-structured, or different type of data, and then you're putting it into, or you're doing some real-time analysis on it, or you clean it up and then you're structuring it so that you can perform meaningful tests to the data. And the thing is, even today, since most of our data is coming from a local or a cloud source, data engineering harnesses the skills or the tools of how to extract this data from these online platforms, and also just to analyze it, extract it, and do meaningful insights from these big data sources. And we have different platforms such as Hadoop, Spark, Kafka, and so on and so on. And it's still using, or the good thing is that data engineering still uses the commonly known languages such as Scala, Python, and R. I don't know if I still have time, because I had a mini hands-on of how to use Databricks.
Yeah, I just wanted to mention that now. I think the recording is going to stop itself soon, so I wanted to suggest if we maybe the talk has been very good so far, but I think if we could wrap it up here and then possibly save the hands-on for another session where we can really get into it instead of having to kind of rush for fear of the recording stopping, if you'd be happy with that, Small.
Nice, fine, thank you.
Yeah, well, thank you. It's been a really, really good presentation. Really interesting to learn about this stuff. I've heard about these topics through my explorations in data science, but they always seem so intimidating and difficult to get started with, but you really made it digestible and easy to get an introduction to and make sense of. So thank you. I really appreciate the talk, and I'm sure the rest of the participants do as well. I think we could possibly squeeze in a few little questions if anyone has any before the recording stops itself. There are any in the chat. But otherwise, in the meantime, I'd like to say thank you on behalf of the participants and on behalf of myself for the great presentation. Yeah, it was very enjoyable. And thank you to the participants. If you do want to catch up any bits that you might have missed, if you perhaps joined a little bit late, this will be on YouTube soon within the next few days, and it'll be in its entirety, so you can catch up anything you missed. And hopefully there will be a follow-up with the hands-on getting started with Databricks and the rest of the Apache and Hadoop ecosystem, which we're very much looking forward to. And thank you again, Small, for the great presentation.
Thank you for giving me the time.
Thank you, Small.